Welcome back for the second and final installment of the APECE Chemistry Chapter 15 Complex Ion Problem Set. Let's take a look at problem number 39. In problem 39, you're told that the maximum wavelength of absorption for tetraamine copper 2 ion is 580 nanometers, and that's in the orange-yellow range. You're asked what color is the solution. This is one that we actually worked with in the lab, and it should be the complementary color. The complementary color to the orange-yellow is a blue color, so this should be blue. Take a look at number 47. 47, you're asked to find what are the concentrations of the copper 2 plus ion, the ammonia molecule, and the complex ion tetraamine copper 2 plus. At equilibrium, when 18.8 grams of copper 2 nitrate, are added to 1.0 liter of 0.400 molar ammonia. You're asked to assume that the reaction goes to completion to form as much copper containing complex ion as you can. That's the tetraamine copper 2 plus. You write an equation. You're taking the copper from the copper 2 nitrate, and putting it with 4 ammonias and making the tetraamine copper 2 plus. The Kf comes from page 442 of the text, table 15.1, as 2 times 10 to the 12th. That equation will come back later. So you got to break this down into parts. There's a lot going on here, but you're given some volumes and masses, and you need to convert those into moles. So you find out that from your 18.8 grams of copper 2 nitrate, you actually have 0.1 mole of copper 2 plus. From your 1 liter of 0.40 molar ammonia, you have 0.400 moles of ammonia. You then assume that the reaction goes to completion, but you'll have to determine your limiting reactant. So you're setting up an ICF table because you have your mole values start. You have 0.1 moles of the copper 2 plus and 0.4 moles of the NH3, and you're going to work forward to create some of this complex ion and then allow the complex ion to dissociate within the water solution. So it'll be minus x, minus 4x, and plus x as you proceed along this, and x ends up being 0.1, so you end up using all of your reactants, and they are in a stoichiometric balance, and then you make 0.1 moles of the complex ion. Then plug that into the an ice table where you have 0.1 over 1 liter, in other words, 0.1 molar of the complex ion, and none of the other two things to start, the other, quote, reactants in this equation. You create 4x of the ammonia, 1x of the copper from that, and you subtract 1x from the tetraamine copper 2 ion. Plug that into your Kf expression, solve out, and actually you assume this x up here is next to 0. Now make sure you plug in 4x and then raise it to the 4th power and solve out proper algebra style to get x is 7.2 times 10 to the negative 4th molar. And that is, in fact, your copper concentration right there. Multiply that by 4, and you'll get your concentration of the ammonia, which is 2.9 times 10 to the negative 3rd. And then you have to subtract, technically, that small value from 0.1, but it's so small that it doesn't actually make a difference, and you have 0.1 molar of your complex ion. Let's take a look at number 53. For number 53, you're asked to decide which statements are true concerning, and then you've given a table of information of KFs and the complex ion. You're asked to decide whether diamine silver 1 is more stable than the dicyano silver 1 minus. You look at the KF values, and that'll be a false statement because the KF for the cyanide-containing thing is so much larger, meaning it's more stable. In part B, you're considering adding nitric acid to the complex ion with silver and ammonia, and asked if it will dissociate the complex ion into Ag and NH4+. Yes, it will. If you add a strong acid to this, it's going to react with the NH3s and break them apart from the complex ion. So that's a true statement. Adding some strong acid, nitric acid, to the AgBr containing complex ion will not have an impact on it. Notice there's no way for the Br to accept H's, as HBr is a strong acid, so it wouldn't actually form. And part D and E, I again copied your complex ion information in KF. For part D, you're asked to try to dissolve AgI, which would be an insoluble solid, and you're adding either NaCN or HCN. NaCN is a better choice because it will fully dissociate. HCN is a weak acid, so there'll be less concentration of Cn-, and it's the Cn- you need to complex with the Ag to actually get the AgI to dissolve. For part E, the higher Kf of the AgCN containing complex ion means that more of that complex ion will form.